Now we want to see the potential energy due to an assemble of charges. What is this? Suppose this is a free space, there is no charge. Free space means I want to say that there is no charge. Now if I bring a charge Q1 at any point, do I have any work to do? Is there any work to do to bring that positive charge Q1 to a free space, charge free space? No. There is no work to done. There is no work to do to bring that positive charge Q1 at that point. Now if we want to bring another charge Q2 at a distance, suppose R1, now we have to do some work for this charge Q1, and that work will be what? Suppose that is W1, that work will be Q1 Q2 by 4 pi epsilon naught R1. Q1 Q2 by 4 pi epsilon naught R1. Now we want to bring another charge Q3. So we want to work, we have to do some work against Q2 and Q1 to bring that charge Q3, isn't it? We have to do some work in bringing that Q3 charge against Q2 and Q3. Q2 and Q1, and that distance, suppose that is R3 and that distance R2. So work done, total work, that will be, suppose that is W2, that will be Q2 Q3 by 4 pi epsilon naught R3 plus Q1 Q3 by 4 pi epsilon naught R2. Now if again we bring a charge Q4, we have to do work against Q1, Q2 and Q3, and the total work will be W equals to Q1 Q2 by 4 pi epsilon naught R1 plus Q2 Q3 by 4 pi epsilon naught R3 plus Q1 Q3 by 4 pi epsilon naught R2, and so on. That is the potential energy, total potential energy, total electric energy, electric potential energy in bringing an assemble of charge to a space. This is a total potential energy, we have to calculate that. Now take, suppose we place a charge Q at point, suppose it is a point A, we place a charge Q here, and the potential of that point is VA, and this is the point B, potential of that point is VB, and a charge whose initial velocity, suppose here is UA and here is UB. So the charge is moving from point A to B due to the potential difference, and its kinetic energy or its velocity increases. So here the total energy of that particle will be what? QVA, if the charge is Q, so QVA plus half m, m is the mass of the charge, half m UA square, and the charge and the total energy at that point B will be what? QVB plus half m VB square. We take it equal from the conservation of energy. So the energy at point A is UA plus half m UA square QVA plus half m UA square, and the energy at point B is QVB plus half m V square. Again I say that a charge is placed in a potential difference A and B. The charge at the initial velocity at the point is point A is UA, and it's moving towards B, and the velocity at the point B is UB. So the total energy at point A will be equal to the energy at point B because of the conservation of energy. So we can see from that expression that Q VA minus VB, that equals to half m VB square minus VA square. So see, you can see that potential difference gives the increase in kinetic energy. That potential difference VA minus VB gives the increase in kinetic energy half m VB square minus VA square. Now suppose VA minus VB is V, we can write that VA minus VB, that potential difference, as V. So we get QV equals to, suppose half m VB is V, that is VB, take VB is V, half m V square, and VA is 0, that is initial velocity is 0. V or UA, here we write UA and UB, so you can write here as UB and UA. Suppose initial velocity is 0, that is UA is 0, and take UB as V, we get QV equals to half m V square. So you can see that V equal to 2 QV, V equal to root over 2 QV potential by m, that is potential. by m. So we get the expression of velocity from the potential difference V, Q and m. Actually, potential, as we have already read that the unit of potential is volt, there is another unit of potential that is called the electron volt, 1 eV. That is called electron volt. That is, if we take an electron, to move in a potential difference in 1 volt, then the potential energy stored on that electron will be 1 eV. Potential is stored in that electron, that will be 1 eV, and 1 eV equals to 1.6. That is the value of the electronic charge is 1.6 10 to the minus 19. Unit is coulomb, and V, coulomb into volt, that is known as the joule. So that will be 1.6 into 10 to the power minus 19 joule. That is another unit of potential, 1 electron volt. Electron volt is another unit of potential. Now we want to know, now we are going to study another point that is called equipotential surface. As we have already seen that for our electric dipole, plus Q and minus Q, that perpendicular bisector point, at any point on the perpendicular bisector point, at any point on that perpendicular bisector line, the potential is 0, isn't it? So if we take a charge Q, suppose we take a charge Q, and at a distance r, there the potential at distance r, their potential is Q by 4 pi epsilon naught r, that we already know. Now if we take a sphere with the radius r, then you can see that on the surface of the sphere, at any point on the surface of the sphere, the potential becomes same. Potential will be same because potential will be Q by 4 pi epsilon naught r at any point of that sphere. So the surface of the sphere, where the potential at all the points of that surface potential is same, that is called the equipotential surface, isn't it? Because we take a charge Q and take a radius r and making a sphere, so you can see that at any point on that sphere, the distance from the charge Q is same, so potential will be same on the any point of on the surface. So that surface is called the equipotential surface. Now there is some characteristics of equipotential surface, that charge on that equipotential surface, if we move a point charge, unit charge or anything on the equipotential surface, no work is done, because there is no potential difference. There is potential at the point P is same potential at the point Q. So if we just want to move a charge plus 1 unit positive charge or anything, any charge, we want to move from point P to point Q, as there is no potential difference, so no work is to be done. So the work is not to be done to move up charge on the equipotential surface, number 1. Number 2, electric lines of force always cross the potential surface perpendicularly. Electric lines of force, that is electric field line, always cross the equipotential surface perpendicularly, that is in that way, perpendicularly. If we take, suppose we take a electric field on that direction which make an angle theta with the tangent to the surface, now we can get that two component of electric field, that is E cos theta here and E sin theta here, that is E cos theta and E sin theta. Now we know that in bringing a positive unit charge or any charge from on that surface to from a point to another point on the equipotential surface is 0. Work done in bringing a charge from a point to another point on a equipotential surface is 0. So work done means what? E cos theta. Suppose therefore E cos theta is the force, tangential force, that is force on the surface, E cos theta, into, if we take a charge from that point to that point on the equipotential surface, that distance, suppose this give the name A and B, so distance is AB, so E cos theta is the force and the distance is AB equal to 0. That means what? That is cos theta equal to 0. So theta equal to 0. So sorry, cos theta equal to 0, that means not theta equal to 0, theta is 90. So electric field always will be the perpendicular to the equipotential surface. Electric field always will be the perpendicular to the equipotential surface. This is the another characteristics. Two equipotential surface never cross each other. two equipotential surface never cross each other, because if they cross, then we get a intersection point, and you can see that on that point there is two direction of the electric field or potential, which is not possible. So two equipotential surface cannot cross each other. These are the characteristics of equipotential surface.